Hello Year 11s, welcome to our second last class for your holiday homework. Okay, so for the chapter 16, today we're dealing with instantaneous rate of change, and this is essentially we're falling towards what actually calculus is and what it represents. Okay, so instantaneous rate of change. So for a function y equals f of x, the instantaneous rate of change for y with respect to x at the point this, so a f of a, okay, just think of that as guys as still your xy, is the gradient of the tangent line to the graph y equals f of x, a f of a. Okay, so what we have is if we have our graph, okay, so y and x, we have our function, whatever it is, and we've got a location, okay, at a f of a. The instantaneous rate of change at that exact point is a tangent line, and what a tangent line is a line that only touches that curve once. Okay, so as far as you zoom in, it actually doesn't touch it any further, and it's a line that just runs parallel to that particular location's gradient at that exact point in time. Okay, and that's what we're trying to find. Okay, that tangent line of what we've got. How do we find that? How do we generate that? Okay. So an example of what we've got, okay, so we need to consider the curve y equals 2x, okay? So using the secant, so remember that curve section that we're talking about within the graph, through the points where x equals 3 and x equals 3.1, okay? Estimate the instantaneous. So what we're trying to do is we don't know how to find the exact instantaneous point, so instantaneous rate of change at an exact point just yet. Okay, we will be learning that. So what we're trying to do is we're trying to find the average rate of change over a very, very small period. Okay, and a very small sort of width that we're finding it. So we're trying to get as accurate as we possibly can without actually using calculus just yet. Okay, so what we need to think about is the graph. Okay, I'm just going to swing my head to the side. Okay, so this is our graph y equals 2 of x. So remember that we've got our y-intercept of 1. Okay, and we've got an asymptote at y equals 0. Okay, so what we're trying to find is we're trying to find the instantaneous rate of change when x equals 3. So when x equals 3, which is halfway in between there, okay, so that's at 3. Up here, we're trying to find the rate of change from there to maybe somewhere like there, so 3 to 3.1. So that width that we're talking about is actually 0.1 units wide. Okay, so what we can do is, what I've done is I've zoomed in. So if you have a look at this graph, I've started this at 3 and I finish at 3.2. Okay, so what we're actually going to be dealing with is from 3 to 3.1. So I've just zoomed in that previous graph as close as possible, and I've only received that section. And as you can see, that line that we have on the graph here, that line that I've got the cursor with, is actually pretty straight. We can't actually tell that it's a curve. There is a slight curve, but from our graph we can't really tell. So that's why we're trying to assume that, because we can't really tell from the naked eye, we're assuming that it's sort of a straight line, and that's how we can get our instantaneous rate of change. So what we can do with our rise and run, okay, so our run is the width, so 3 to 3.1, and our rise is whatever the value of 3 is, and when we put that into the formula, when we put 3.1 into the formula. So what values do we get? Okay, the values that we get, okay, 2 to the power of 3 is 8. 2 to the power of 3.1 is 8.5742. Okay, so now that we have these coordinates, okay, we have those coordinates that I've listed there, what we can do is we can actually find the gradient between those 2 points, very small points. So when x equals 3, y equals 8. When x equals 3.1, y equals 8.5742. Okay, to find the rate of change, trying to move my head, trying to find a spot where I can. There you go. We get 5.7419. Okay, so when we find the gradient, so we go, so that's essentially our y2 minus y1 over x2 minus x1. Okay, so this is part of the reason why all of this linear graphs that we dealt with at the start of the year is very important. Okay, our next example, I'm going to move back down here, hopefully it's safe. We're going to repeat the steps, but instead of using 3 and 3.1, we're going to get it even smaller, a lot smaller. So we're going between 3 and 3.001. So our width, so as we see our curve, our width is actually 0.001. So it's actually very small. So hopefully we can get a more accurate answer. Okay, that's what we're trying to hope for. Okay, so when x equals 3.001, y equals 8.005547. So that's just simply as we had before. So 2 to the power of 3.001, and that's how we generated that value right there. Okay, to find our gradient, okay, we're still doing our y2 minus y1 over x2 minus x1. So find the gradient, and we actually get a gradient of 5.547. So if we try and compare the solutions between this question and the one before, so we had 5.7419 as we went back. As we go forward, we get 5.547. So our gradient is actually getting lower. What's actually happening is that we're actually becoming more and more accurate. Okay, the actual true instantaneous rate of change is 5.5452, and in a few weeks you'll actually be able to calculate that yourself. Okay, what we're trying to do is, as we shrink the run that we're using, okay, so as we shrink the run, okay, as we get smaller and smaller and smaller, our answer is actually becoming more and more accurate, and that's what we're looking for. Okay. So as we get that, so we get 5.5452, and that's to 4 decimal places. Okay, so what you can do, I'll rub out, erase all that from the top there. Okay, what you can do is you can answer some questions. Okay, so hopefully that makes sense. Just remember that it's essentially we're treating it like a linear graph. We're just using it within a very small run. Okay, so you can do questions 1, 2, 3, 5, 7, 8, 9, 10, and 13. Okay, so work through those. Once you've completed those questions, you can move on to the 16E video. Okay, thank you for listening.